So in our studies of reflection in mirrors, we've kind of talked about the basics of reflection, some of the principles when we look at images like magnification, attitude, position, type. We also looked at for concave and convex mirrors, if you have an object placed in front of them, how do you draw the ray diagram to determine the image and the characteristics of the image. But as I mentioned, when we draw ray diagrams, we're not drawing them to actually get an exactness in our answer. They're more like a rough check to help make sure that we're on the right path. With physics, usually there's some math involved in it. So we've done kind of what we'll call the graphical treatment of mirrors. We're going to start to look at the mathematical treatment of it. So the mathematical treatment, now, there's in years past, I used to show how the equation was derived. I found that that's not particularly useful. If you want to look that up online, go for it. You'll find it all over the place. But we have an equation that we use for mirrors that relates the distance of the object from the mirror, the distance of the image from the mirror, and of course, our lovely focal length. So the equation that we have here is this 1 over dO plus 1 over di equals 1 over f. So the big thing is we have a lot of these inverses. So this is known as the mirror equation. This is going to be the math. So as I mentioned, dO, it's that distance of the object from the mirror. Di is the distance of the image from the mirror. And f is that focal length of the mirror. So like for example, if I'm going to use this concave mirror here. Here's my focal point. So since we just did a sketch like this, there's my object. Maybe here's my image over here. Something that looks a bit like this. So we already know that's my focal point. So we know the focal length is going to be that distance between the actual focal point and the mirror itself. So then dO is going to be that distance between the object and the mirror itself. And then di is going to be that distance between the image and the mirror itself. Now remember, for real images, the image will be on the same side of the mirror as the object. Now, you'll notice that I don't have any units here. And the reason for that is there's no hard, fast units that you actually have to use for this equation. As long as the units are the same on dO, di, and f, it doesn't actually matter. So all we just want is the same units for it all. So the same units for dO, di, and f. You could use the meters if you want. But more traditionally, what you're going to find is that dO, di, and f, they're in centimeters, just because that's the more appropriate scale for most of the applications that we do with mirrors, and as you'll see a little bit later, lenses. But the units don't matter. As long as they're in the same units, you're good to go. So the mirror equation, it looks a little simple and complicated because of those inverses, but it actually tells you quite a bit. And as I mentioned, the units are really flexible. We also have another equation that gets used for examining mirrors. It's how we get this is through some geometry and all that. Again, I'm not going to show you that, but we have this hi over ho equals the negative of di over do. So hi is going to be the height of the image, ho is going to be the height of the object, di and do are just the same as last time. Di is that distance of the image from the mirror, do is that distance of the object from the mirror. Again, you'll notice I don't have any units. This equation is also very forgiving. All the units have to be the same, but they can be in any units. Again, traditionally, we like to use centimeters. That's just kind of how it is. But if you use meters, not a problem. So all of these variables, we can kind of see this on a diagram below. So again, we have like this object here. We have this image that's formed. We have our focal point here. So again, that focal length is that distance from the focal point to the mirror. DO is that distance from the object to the mirror. DI is that distance from the image to the mirror. And then when we're looking at HO and HI, HO is sort of that vertical height of the object. HI is that vertical height of the image. Now in all of these, we might ask ourselves, well, how do I account for something being in front of the mirror, being behind the mirror? How do I account for an object being upright? How do I account for it being inverted? Well, good question. So with the mirror equation, it's very much kind of like all the vector stuff we've done in the past in Physics 20 and in the momentum unit. The sign gives you an indication about what your answer represents. So with the mirror equation, we actually have to be really careful with the sign. So we do have some rules with the sign convention. I realize there's a lot, but these are really, really important. So first of all, real images, they are going to have positive distances measured from the mirror. And objects are always going to be real. You either have a physical object or you don't. You're not going to have a virtual object. Virtual images are going to have negative distances measured from the vertex. So if you happen to get a DI that's negative, that's right away telling you that you have a virtual image. So anything that is upright or erect, it is going to have a positive height, so HI is going to be, or sorry, whatever, if you're using HO or HI, depending if you're talking about the object or the image. But in this case, I guess we're looking at images, so HI is going to be greater than 0. An image that's inverted, it's going to have a negative height, so HI is less than 0. Now, here's the real sticky point that gets students in Physics 30. So concave mirrors, they have a real principal focal point, and for concave mirrors, the focal length is a positive number. For convex mirrors, they have a negative virtual focal point, or sorry, they have a virtual focal point, so their focal length is negative. Now you might say, what's the problem here? Here's the problem. When they're talking about a convex mirror, they're not going to tell you the focal length is negative. They might just say, on this convex mirror, the focal length is 20 centimeters. When you're using the mirror equation, you have to know to put in that negative. And that really gets a lot of people, and that's also a common trap on diploma exams. They'll like to talk about convex mirrors. They'll give you the focal length as an absolute value, and then students forget to put in that positive. So be really, really, really careful with that. I know there's a lot of sign rules here, but if you're really careful with the sign rules, the mirror equation and the HI over HO equals negative DI over DO, that will give you everything that you need to know. And if you're ever unsure about your answer, draw a ray diagram. You'll confirm your answer really quickly. Now, the last thing, when we talked about magnification of the ray diagrams, we kind of did that more by inspection. We can absolutely do this by mathematics. So the magnification, little m, it's going to be that ratio of either the image height to the object's height or the negative of the image distance to the object distance. So we have this m equals HI over HO or negative DI over DO. So you can use either m equals HI over HO, or you can use m equals negative DI over DO. Whichever one is more applicable to the information you have, go for it. Just to note, that negative sign in front of the in front of the DI over DO, that is there more as a consistency measure or more of a mathematical thing. It's just to ensure that all of our sign conventions stay consistent with one another. So with magnification, if our absolute value of the magnification is less than 1, this is going to tell us the image is diminished or smaller. If the absolute value of the magnification is equal to 1, the image is of the same size and has not changed. And if the absolute value of the magnification is greater than 1, then we have a bigger image or we have an enlarged image. So in the next couple videos, we're going to look at some different examples of the mirror equation in use. We'll show you some tricks, some traps, but we'll go through this equation in some good detail.